Hello students, welcome to this lecture on studying timing analysis. In this particular lecture, we will take a look at some of the examples of the combinatorial circuits within the two, it is there in between the two flops, so that it is a timed circuit output. And few some parameters for the 65 nanometer technology node utilize those setup timing parameters, and then the combinational circuit propagation delay parameters, and then try to design a clock so that it doesn't violate the setup time. And in this lecture, we'll also look into the hold time failures and proceed further for the flip-flop designs. Right, so it is going to be a purely a flip-flop designs. Use some of these parameters for the flip-flop designs, and then try to identify what should be the clock time period, and if it doesn't match properly, then what are the failures we should analyze. All right, so moving ahead, so let's say this is one of the designs which we had seen in the last lecture, where we had the flop 1 and flop 2, which is driven by the same clock signal. So let me also pick up my pointer, and in between we have the combinatorial circuit. It will have its own propagation delay, and the flop is characterized by the setup time and then the propagation clock to Q. Similarly, flop 2 will be characterized by the setup time as well as the propagation clock to Q, as well as the hold time for both the flops will be characterized. Let me take this particular clock signal, and then the first clock and then the second clock, and then the D1 is arrived much earlier than the T setup time for the flop 1. And let's say that the Q1, the output of the flop 1 is evaluated, or it has reached, or a steady state of Q1 has been attained after the propagation clock to Q1 of the flop 1 design. And post that, it is given the input to the combinatorial circuit 1, so it will be the propagation delay 1 of the combinatorial circuit. So the output which goes to the D2 of the flop 2 input has reached after the propagation delay of the combinatorial circuit 1. And let's say that this has arrived much earlier than the T setup time of the for the second rising edge of this flop 2. Then we have this particular expression, which is TPD, which is should be smaller than or equal to the clock time period minus TPCQ1 and then T setup. Right, where this is called as a maximum delay constraint. So what it really means is the combinatorial circuit design number 1 this has to be designed in a way that this TPD value, or whatever TC minus TPCQ plus T setup, is the maximum propagation delay it has to be designed with. So that is the maximum delay constraints for the combinatorial circuit number 1. Right. TPCQ plus T setup, it is a characterized parameters which is taken from the standard cell libraries. So it is nothing but the sequencing overhead parameter. So it is basically an overhead parameter of the flop 2 and an overhead parameter of flop 1 to TPCQ and T setup. And it is called as the overhead because it is it takes its own time. Flop 1 will take its own time, so that we will get the output of the flop 1, and then flop 2, for the flop 2, the output of the combinatorial circuit 1 has to reach before the T setup time. Right, so this becomes kind of an overhead for the combinatorial circuit design. So that's why it is called as a sequencing overhead. But we cannot avoid it because we need the sequencing to be generated, because we need the output of the combinatorial circuit to be timed. Right, so in that sense, it is a sequencing overhead. So hope it is clear. Moving further, let's take a typical example for digital blocks, where we have the this series of the combinatorial circuits blocks, like the adder, muxes, bypass muxes, late bypass muxes, and which is given to the same flops. So we don't have flop 1 and flop 2 and flop 3 as such. What we have is the same flops design, and the output of this combinatorial circuits is kind of it has to be evaluated at every clock edges, or at at different clock edges. Right, so if if I consider the flop 1 the first clock edge, so it will have its own overhead like the TPCQ. So the output will be generated after the TPCQ 1, and then it's a series of combinatorial circuits will give give the output here. and it should reach to the second clock edge just before the T setup time, so that it should give the output here after the TPCQ of the second clock edge, and then similarly it will keep on pumping the output back to the input of the flop designs, and then once again the computational output will be provided in the third clock edge, fourth clock edge, and then so on. Right, so let's say that the flop is kind of characterized with this parameters: setup time of 62 picoseconds, hold of 10 picoseconds, TPCQ propagation clock to Q of 90 picoseconds, and contamination clock to Q of 75 picoseconds. Right, so we will come back to this T hold and contamination delays a little bit later, but we'll try using this setup and TPCQ because we have anyway seen the maximum delay constraints. And the propagation delay of this adder block, result muxes, bypass muxes, and a late bypass muxes are given in here: 590, 60, 80, and 70 picoseconds respectively. Its contamination delay parameters are also given, but I think we will have a look at it at a later stage. And if I just go by the design requirements or the specifications, we can easily see here that the TCD value is actually less than the TPD value. Right, so the 100 picoseconds is less than 590, 35 picoseconds is less than 60, 55 picoseconds is less than 80 picoseconds, and 45 picoseconds is less than 70 picoseconds. And intuitively that makes sense because the contamination delay is always less than that of the propagation delay. The question here is what should be the clock that we need to design, right? And what should be its minimum duration so that we don't violate the setup time failure. Right, so if I remember the clock, we have the clock, and if I consider the positive edge clock, we have to ensure that within the sequencing overhead, the combinational circuit, the propagation delay of the combinatorial circuit blocks here should be reached before the T setup time, and this TPCQ will be there for the flop to throw the output. So this will determine my clock duration. So if I look into the clock duration here, it will be nothing but the minimum clock duration, so that we don't get into the setup time failure, will be nothing but the addition of all these three components. The three components are this will be TPCQ of the first flip-flop. This will be the T setup of the second flip-flop. Here both the flip-flops are the same. Right, and then this will be the combinatorial circuit propagation delay value. Right, so moving ahead. So if that is the case, what we have seen is TC should be greater than TPD plus TPCQ plus T setup. That is what we had seen, and TC minimum will be nothing but 90 plus 590 plus 60 plus 80 plus 70 plus it should arrive before the setup time, at least before the setup time of the second clock. So I will get 590 plus 60 will be 650 plus 150 will be 800, 890, 952. Right, so this is what we'll get. 952 picoseconds should be the minimum clock time period, so that we don't get into the setup time violation. So for the circuit to operate correctly, right, it should be greater than that. So if I choose 100 picoseconds, that is very well good. That will be better, but it should not go below 952 picoseconds. Right, moving ahead, let's say that the clock time period is 852 picoseconds. Then what is the problem? Right, so remember that if it is 852 picoseconds, and as we had seen earlier, let me draw that again. So if I have a clock time period, right, so this TPCQ and propagation delay of all these three combinatorial boxes. Let me try to erase this, and then this T setup time. So all these three parameters, right, requires 952 picoseconds. That is what we had decided in the previous slide. But now what if the clock itself is short? So what if the clock itself is short here, 852 picoseconds, then what happens? Right, so if I take this clock and then this clock, instead of 952, it is 852 picoseconds. right? We were supposed to have 952 picoseconds, but whatever, we have 852 picoseconds, right? So my output, in fact, I need to determine where this combinatorial circuit output will reach and whether it will violate the setup time failure. Right, moving ahead. So this is what my timing diagram will look like now for 852 picoseconds. So for an 852 picoseconds, the first stage and the second stage I have written, and then from the first stage I'll get TPCQ of the flop for this one, and then it proceeds to the combinatorial circuits, 4 blocks, and then the output which will be fed as an input to the flop. So that is what I've written here. D, it takes 590 plus 60 plus 70 plus 80, so it is 90 here, TPCQ from the flop, and then the combinatorial circuits addition of the propagation delay, which will be 590 plus 60, which will be 650 plus 70 plus 80, which will be 800 picoseconds. So this, the total will be 800 picoseconds, right? So 800 plus 90, so it will be 895, and 852 is what the clock duration is, so it is likely to pass. The output of the late bypass mux is going to surpass the second clock edge, right? In fact, it is going to surpass the second clock edge by 890 minus 852, which turns out to be 38 picoseconds, right? So what is likely to happen is, 38 picoseconds doesn't fall in the T hold the time duration. So if I consider the T hold time duration, which is the T hold, which is 10 picoseconds after the rising clock edge, so it surpasses that 10 picoseconds also, so it is 38 picoseconds. So this particular output of the combinatorial circuit, which is given to the flop, which will be captured now not in the second edge but in the third clock edge, right? So it will not have any setup time failure effects. The setup time failure effects happens only if my output actually reaches somewhere, in between the setup time duration and then the clock edge. So if the setup time duration in the previous case, let's say that the setup time is 62 picoseconds, right? So so if it reaches somewhere between from the clock edge to the 62 picoseconds so if I have a clock edge here and this is my 62 picoseconds, right, but my output actually reaches somewhere in between this, then we have this setup time failure. But in this case, it is actually not doing that, and in fact it is reaching much earlier with respect to the third clock edge, and it is reaching much later than the second clock edge, right? So in that sense, it is not having the setup time failure. All right. So the other question is, if let's say if the TC is 885 picoseconds, whether it is going to have the setup time failure and then the hold time violation. Again, the 885 picoseconds, I need to draw the clock diagram and then find out my output of the late bypass mux, whether it is reaching near the second clock edge or what. So if I do that, so this is my clock of 885 picoseconds of the duration. So the second clock edge is going to arrive after 885 picoseconds of the first clock edge. And if I consider this 90 picoseconds of TPCQ and then the remaining, this will be our 800 picoseconds. So 885 and 800 plus 90, which will be 890. So it is going to arrive after 5 picoseconds after the clock edge, the second clock edge. So it is not arriving 5 picoseconds before the second clock edge, then it will be a setup time violation. So now it is arriving after, so it is not the setup time violation anymore now, right? So, but it is having a hold time violation. The reason is the hold time is of 10 picoseconds. So it is not arriving after 10 picoseconds, but rather it is arriving before the 10 picoseconds. So it is arriving after the 5 picoseconds to the clock edge. Right, so it falls in between that whole time, and then the data can actually get sneaked in to the output. So the setup is not violated, but the whole time is violated, right? Because what we are assuming is that because the setup is not violated, so this particular clock edge will now be captured at the third clock edge. But rather, because the contamination delay or whatever, whatever the output it can pass here, this gets sneaked in within this, the 5 picoseconds or the 10 picoseconds window of the T hold time, and some of the output can get captured into the second clock edge. But whereas the setup time is not violated, what it means is the output should be captured in the third clock edge. But here, because of the hold time failure, some of the outputs can get captured in the second clock edge, which is not correct. So it will be very, very inconsistent in the sense some of the output will be captured in the third clock edge, and some of them will be captured in the second clock edge. So that is, that's not right, appropriate design. So we need to ensure that this particular output is changing only after the second clock edge and its hold time. So we may have to add a buffer here, right, which will give some more delay, and that delay is going to it's going to avoid the hold time failure, right? So in that sense, I will not have a hold time failure, I will not have a setup time failure, and then we can consistently or confirmly or confidently say that the output will be captured in the third clock edge. The output which is captured in the first clock edge will be captured in the third clock edge, and then it will be captured in the fifth clock edge, and then so on, right? So what we really need to do is we need to once we design a circuit, we will have to make the confirmations that both the hold time failure as well as the setup time failure are avoided. If one of them is violating and if other is not violating, then also we'll have a problem. If both of them are violating, then also we'll have a problem. What we need to ensure that is both of them, both the static timing analysis or the constraints like the setup time violation as well as the hold time violation doesn't occur in our design. Right? Hope this is clear. Right. So let's I'll just introduce you to the minimum delay constraints for the flip-flops. Right, what we have seen is a maximum delay constraints. Now, for a combinatorial circuit, what is the maximum delay constraints that we know? That is actually a function of the clock time period and then its parameters, propagation, clock to Q, and then the setup time. Right. So the minimum delay constraints is about what should be the minimum delay. What should be the minimum delay for the combinational circuit so that it avoids the hold time failure. Right. So if I look into this particular design, it is nothing but the same clock is given to the flop 1 and flop 2. D1 signal is given to the flop 1 so that I'll get the Q1 output, which is given to the combinatorial circuit 1. And then the output of the combinatorial circuit 1 is fed to the flop 2 design. Right. So if I draw the clock here, and then remember that these flops are for the rising edges. So these are for the rising edges of the clock, right? So my clock is like this. So my Q bar or the clock bar signal, because there will be some delay for the clock bar to be generated from the clock. So that is when the hold time failure is likely to occur, or the hold time itself is actually defined by the difference between the clock bar and the clock signal, or whatever the propagation delay for the clock bar from the clock source, right? So that propagation delay is nothing but the hold time. And let's say that the D1 has arrived earlier, so that it is quite stable and it has arrived before the setup time of the flop 1 design. And then Q1, so the Q1 coming from the flop 1 and it is coming really fast. It could be due to the contamination output, contamination clock to Q output. And here I have not taken propagation clock to Q, it is the contamination clock to Q. And if it is a contaminated output here, which occurs, and this contaminated output goes to the propagates to the combinational circuit through the contaminated output here. And let's say that the combinational circuit has 10 inputs, but not all 10 inputs are changing, only one input is changing. In that sense, I'll get a fastest output here. So that fastest output, we can say it is a contaminated output because this is a contaminated input coming to the combinational circuit, and then we'll have a contaminated output, or it can be specified or characterized by the contamination delay of the combinatorial circuits. And so we will have contaminated output here, which, if at all it reaches before the T hold of the flop 2, right? If it reaches before the T hold of the flop 2, right, then we will have a problem. Okay, so let me try to explain this again. Flop 1, we are expecting the input to be captured, the output should be capturing the input in the first clock edge. Flop 2, what we are ideally expecting is D2 will arrive. D2 will arrive after the hold time of the clock 1, so that it will be able to capture consistency in the clock 2 signal. But if the D2 signal arrives, whatever it is, the contaminated output or the propagated output, propagation delay output or the contaminated delay output, if it reaches before the hold time of the first clock edge, right, then the flop 2 is likely to capture, it might actually get sneaked into the Q2 signal. So the Q2 will be appearing in the first clock itself, rather than what we are expecting is that it will come into the second clock edge. But because of the contaminated output coming from the flop 1, or the contamination clock to Q delay output, and then the contamination delay of this combinatorial circuit, there is a likelihood that if both of them, if it appears, if it is really small and if it is smaller than the t hold time of this particular flop 2s which we have used, then my Q2 can get actually sneaked in the first clock edge itself, which is not good, right? So what we are expecting is, from the setup time, we are expecting that it will arrive in the second clock edge, but the contaminated output can actually sneak into the first clock edge itself, so which is kind of violating. So it is violating the hold time failure. So what we really need is the combinatorial circuits contamination delay, right? And the flop 1's TCCQ, both this one and this one, addition of this should be greater than the T hold time which we have, right? So what we need is a TCCQ plus TCD should be greater than or equal to T hold. So if that is the case, TCD, if it is greater than the T hold, then we are rest assured that Q2, although D2 is we get a D2 signal which is very, very fast because of the contamination signal coming from flop 1 as well as the TCD of the combinatorial circuit, but still it passes it comes after the T hold time, so it cannot sneak into the output. So the sneaking in is possible only in the second clock edge. So it will pass only in the second clock edge. So my T hold time, whatever it is kind of a characterized from the flop designs, so standard cell libraries. So we have to ensure that TCD plus TCCQ should be greater than or equal to T hold time. TCCQ is from the flop designs is again a characterized parameter, so we don't have much of an allowance to design. What we can have a different design is the TCDs. So TCD is a design parameter. So we have to design a combinatorial circuit such that the TCD is greater than or equal to T hold minus of TCCQ. And we'll also have to come up with a combinatorial circuit design such that TPD, right, the TPD propagation delay should not violate the setup time failure, right? So the combinatorial circuit designs now have two constraints. One is coming from the setup time failures, avoiding the setup time failures, and then another constraint is coming from the hold time failures, right? So the setup time failures will give us the maximum delay constraints, and then the hold time failures here gives us the minimum delay constraint. So if I write TCD, it is actually T hold minus TCCQ, right? So the minimum delay that it should have, the combination circuit should have, so as to avoid the hold time failure, is T hold minus TCCQ, right? So that should be the minimum delay. Right, hope you are able to understand this.